journey in condensed matter physics, and I hope it will be for you too. So my lectures will be about out of equilibrium dynamics in correlated systems, in particular strongly correlated systems. And I'll formulate them in a very general way, but we will always have in mind applications such as high TC, and in particular the strange metallic phase of high temperature superconductors. So I'd like to ask a very general question, which is the response of a system initially in equilibrium to external perturbations. Okay, so originally the system will be described by maybe a Gibbs state, or if you're keeping track of some other conserved quantities, you might have some other density matrix, but by some equilibrium states. And we'd like to study the response of the system to external perturbation or probe, such as electric fields, changes in temperature and magnetic field, in chemical potential, which you could get from doping, or in-plane fields, or so on. This is a very broad question. In a sense, it's almost all of condensed matter experiments. But we'll limit it in a little bit. And so these probes, what they're going to do is that they're going to take the system out of equilibrium. Okay, turning them on amounts to activating terms in your Hamiltonian that will depend on time. Let me write things in continuum notation, but it's not too important. This is my probe. And probes generically couple to some operators of your system, and they will turn on new terms in your Hamiltonian that depend on time. And that will take your system out of equilibrium. Okay. So in general, this would be a complete mess. But what we're going to do is we're going to focus on small probes, small perturbations. Okay. This is why we'll always be only slightly out of equilibrium. This is where we can hope for some kind of universality. And so in this case, for small probes, we can expand. So expanding in these probes, instead of a complicated out of equilibrium calculation, one is led to study observables. One is led to evaluate correlation functions in equilibrium. Okay, that will involve these operators that we've excited. Okay, so here I'm imagining the time evolution, the time evolution unitary. It will have each of the this and the exponent, and I'm expanding in these probes. We're considering small perturbations of our system. And expanding in these probes, we'll be left with an equilibrium thermal density matrix. Okay, so this object here, I'll give it a name, can either be viewed as a response to out of equilibrium response to external probes, or as an equilibrium correlation function. Okay. Let's say a dynamical correlation function in equilibrium, or as a slightly out of equilibrium response to external probe. And one example that you all know of this is the conductivity. Let's say the optical conductivity, which you could either view as a out of equilibrium, slightly out of equilibrium response of the current in the presence of electric fields. So the leading linear response would look like this. You would have other nonlinear response that you heard about. Or you could also view the conductivity is also an equilibrium property that measures current fluctuations in the thermal states. Okay, and this correspondence goes beyond linear response. If you're interested in nonlinear response to external probes, these will correspond to higher point functions of operators in thermal equilibrium. So these are our target is to evaluate things like this. Yes, question. Yeah.
This is written Hamiltonian, right? This is just a function of operator at x.
We'll be interested in correlation functions of operators at different time. Dynamical correlation. Yeah. Yes. That's right. That's right. That's just the operator at. Yes, the Hamiltonian will depend on time.
And to phi on time.
Yes.
Operator that couples to is just like, if I'm doing, that should just be O of x.
Right? The operator that couples to, I think, will be O of x and t. It couples to the.
What you want to evaluate later on is, Heisenberg operators.
Let's see. I think you need a t here, but we can negotiate later. Yeah, otherwise you wouldn't have different times in the correlation function. So these objects, so this is the type of objects that we'd like to compute. Now they're okay, needless to say, they're very challenging to study in interacting theories. From microscopics. In fact, even at weak coupling, there's typically, at finite temperature, there's typically a breakdown of perturbation theory, which allows for the emergence of interesting collective phenomena like hydrodynamics. And so even in weakly coupled theories, it's a lot of work to actually get, to evaluate these observables at late times. Not to mention strongly interacting systems where there's really, you typically don't have controlled approaches to evaluate these things from microscopics. So microscopics is great when you can do it. It can give you an idea of things, but in some situations, it doesn't suffice. And so the point of these lectures will be to develop non-perturbative methods to study these objects. Okay, and in particular, we'll study effective field theories for fluctuating hydrodynamics. And in the last lecture, we'll talk about universal transport bounds. Okay, that are obtained regardless of microscopics. So that's where we're going. Any questions? Yes. Yes. Oh, how would you do it experimentally? Okay, we'll see that. Yeah. Other questions? Yeah, we're going to do chemical potential now, and you'll do temperature in the exercise. That's the notes should be online. Yeah, soon. Other questions? Okay. So before we talk about out of equilibrium physics, let's start with very briefly about equilibrium, response to static probes, static or time-independent probes. As a warm-up. Okay, and just one technical point that I want to make before that. So the correlation functions that we're going to be interested in look like this. Okay, they're correlation functions involving operators at different times and different points. But a type of correlation function that you've probably seen deal with, that you've probably seen in Andrei's, in Chubukov's lecture or Maslov's lecture, are imaginary time correlation functions. I'll briefly remind you what these are. So if we analytically continue our correlator over there to imaginary times, or what's often called Wick rotate, then imaginary time correlation functions have a nice path integral representation on what's called a thermal cylinder. Which is very cool. Where time becomes a circle of length beta, and then your space is whatever it was. I'll be in the continuum just for simplicity, but that's not too important. You could replace this with whatever you want. So that what I mean by this is that imaginary time versions of these this correlation function you can derive a path integral representation for it in the usual way that you derive path integrals. You separate time evolution into many small steps, insert a complete resolution density, and what you'll find is a path integral with the Euclidean action on the thermal cylinder. Okay, and the thermal cylinder appears because of this trace, right? So here we have this density matrix, this thermal density matrix, which is like evolution in imaginary time by I beta. So we have a circle of length beta. And then the trace identifies the fields at both edges, so imposes periodic boundary conditions for bosons, for example. Okay. So this is a kind of mapping between thermodynamics in quantum systems in d dimensions and stat mech in d+1 dimension on a cylinder. This mapping is very useful. For example, Monte Carlo numerical studies use this a lot. Okay, so so to generate correlators like this, what we're going to do is that we're going to couple, that was one of the questions, we're going to couple our system to sources and build in this way a generating functional. So to generate such correlators, we're going to couple operators of interest to sources. So this is just a theoretical construct that we're doing here. And to illustrate this, I'm going to consider as an operator of interest just the density. And you'll generalize this. But you could really do this for any operator you care about, currents and so on. Yeah. So this object wouldn't make sense without time ordering. One way to see this is you insert a complete base of energy eigenstates, and you'll see that it blows up if time doesn't increase along. e to the, beta, e to the tau times e contributions, tau positive, and that they'll blow up. Left-hand side doesn't exist. Any other questions? Yeah.
What, real-time correlators?
Yeah.
Continue later?
Yeah. So we'll talk about that. The most of this will be about real-time correlators. But let me first talk about time independent, and we'll talk about analytic continuation, and we won't be happy with it. That will be part of the point. Okay, so let's generate correlation functions of. So we're going to consider a generating functional, the source that couples to charge density mu, copotential, and I'll consider the following object. So I'm only going to consider time-independent chemical potentials. We're doing equilibrium physics for now. Okay, so this is generating functional. Clearly taking derivatives of this, so maybe let me first say, if I turn off this chemical potential, or if I just set it to be a constant, I'll recover the state we had before. Okay. But here now we have a more interesting object that depends on this mu of x function. Okay. So if mu is a constant, then z would just be trace e to the minus b. Okay, but here this will be a richer object. And let me also define, so the true generating functional is the log of this. Okay. So this w, this generating functional w, generates static connected correlation functions. Or said differently, correlation functions of time integrated operators. Okay, for example, the second derivative of w with respect to twice this function is going to bring down, so we'll have two integrals over the thermal cylinder. So I'm taking two derivatives and then I set the source to be constant or zero, okay? And so that at the end of the day, I'll have just the equilibrium thermal density matrix and two density operators. Okay, one of the integrals will just give you a factor of beta because there's no dependence on the time difference. And the other integral will select basically the zero frequency, or rather the zero Matsubara frequency component of the Euclidean charge Green's function. Okay, and these are all connected correlators. So the Euclidean Green's function is, I'm defining it to be connected. So it's going to look like this. Okay, is this clear? Okay, so now why am I doing this? So this is just a way to repackage things. And you might worry that it's completely useless because this will just be a horrible beast, right? It's a function of a function, mu of x, it's a functional. It could depend on, there are many ways it could look very horrible. But we're going to be saved by the fact that most systems have a finite thermal correlation length, which will imply that this functional has a local expression in terms of mu. Okay, so most systems have a finite thermal correlation length. What this means is that static correlation functions decay exponentially in space at long distances. They are smaller, at least decay exponentially. Okay, and when this is the case, what we can do is that we can integrate out everything, all of our degrees of freedom, and we'll be left with a local effective action for the sources. Okay, because the matter is in a sense gapped, or rather short range. Okay, so if this is true, integrating out everything produces a thermal effective action that is local in the sources. In this case, just mu of x. What does local mean? Well, it's going to have a derivative expansion suppressed by the correlation length. Okay, correlation length times spatial derivative is dimensionless object, and this is what we'll expand in. Yes, questions? Yeah. So here I'm talking about thermal dynamics. So whether it's gapped at zero temperature won't matter too much. Okay. Yeah. So there are very important cases that don't satisfy this, and I'll talk about them. Yeah. Yes.
Yeah, I was also asked.
Yes. Okay.
So what kind of system does it actually include, like
Yeah.
critical systems?
That's right.
Systems?
So okay, maybe I'll talk about it now. So there's two notable situations where you don't have a finite thermal correlation length. What are they? Or there's several. Can you come up with some? Long range interactions? Yeah. Other situations? Spontaneous symmetry breaking? Yeah. So if you have okay, let me write. So let me start with this one, spontaneous symmetry breaking of a continuous symmetry. Okay, an ordered phase. What happens there is that you have goldstones, which have power law decaying correlations. Okay, so they don't satisfy this thing. We will talk about ordered phases as well. What you would do here is that you would actually keep them in your thermal effective action as degrees of freedom. You wouldn't integrate them out. Okay, we'll see examples of this. For now, I'll assume I'm in a disordered phase. Other examples? Critical, yes. So if you have a classical, thermal continuous thermal phase transition. Okay, here famously the correlation length diverges. And the story here is a lot richer. You have interesting, a lot of nice physics, critical exponents. I won't be talking much about that, but there's a lot of interesting work, even classic work on dynamics in these situations. And I also won't be talking too much about unscreened Coulomb. Okay, so those we will include some of them, but for now I'm just going to assume I'm not in one of those situations. Other questions? Yes. No, the density field is always bosonic, so it always has periodic boundary conditions. But this could be fermions. Yeah. No, reasonable fractionalized phases would satisfy this.
Did you have like photon power?
No, but the photon can get a thermal mass. So QCD, for example, the fields get a thermal mass. How to see that perturbatively can be very difficult. Okay. In fact, in QCD, it's famously a strongly coupled problem. That for photons, it's easier, but in QCD, there's some components of the gauge field for non-abelian gauge fields that perturbatively doesn't get a thermal mass, the magnetic part, and so perturbatively it doesn't, but non-perturbatively it does. And you need numerics or something else to see. So it's believed to be, a very generic situation, which has a class of counterexamples. But yes, the probe. That's right. So there's nothing left. Yeah. Okay. So as long as I'm not in one of these situations. The expectation is that a local system should have a finite correlation length. And then this generating functional is local. Let's write what it should be, what it can be. So we're just going to write down the most general thing we can in a derivative expansion. Okay. So first thing is that it could just depend on the chemical potential locally. So I'll write this in this way. Okay. Now this is no longer a functional; it's just a function of the chemical potential integrated over space. And then I could have higher derivative terms. Higher and higher derivative terms. There's a scale separating these two terms, which is expected to be of order the thermal correlation length. Okay, this finite thermal correlation length is what is allowing for this derivative expansion. Okay, so here we have some coefficients that are unfixed. They're sometimes called Wilsonian coefficients. And we'll see that this thermal effective action has some predictive power, even though it has these unfixed, unknown parameters. Okay. The first one is actually one that that has a better name. It's basically called pressure or free energy. Yes, the question.
They're only fixed, we don't know how to integrate it with degrees of freedom, right?
We don't know. Yeah, they're hard to compute from microscopics. You'd have to compute that. I'm not telling you what they are. They're not equal to 3 or something. Yeah, they're
given some theory.
They're
fixed by the theory.
Sorry, they're well defined. Yeah. So pressure, the equation of state is a well-defined thing of any system. It might be hard to compute, but it certainly exists. If it's not density, if mu is not density, it wouldn't be pressure. That's right. That's right. Yeah. It probably wouldn't have a name because it would depend on what operator. If mu was, yeah, if mu was spin density, I think it would still have the interpretation of pressure. But if, yeah, if it was a current or some other, bilinear of fermions that has some dressing, yeah, it wouldn't have the interpretation of pressure. It would still exist, but it would just not have a name, maybe. To see that it's pressure, let's consider just the simpler situation where we set our probe field to be constant. And in this case, all the higher derivative terms in the thermal effective action die because mu is 0. And our thermal effective action just gives us beta times F0 times volume. Okay. Sorry, there's no factor of beta. Okay, and taking derivatives. Of this functional with respect to the things it depends on, chemical potential, for example, log z. This will give you charge density. Yes, thanks. So taking derivatives of this object with respect to, let's say, chemical potential first will give you charge density. Taking derivative with respect to beta will give you some combination of energy density and charge density. Okay, and you can check that these are the reactions that pressure satisfies. Okay, the usual thermodynamic relations, which relate derivatives of pressure with respect to chemical potential or temperature to energy density and charge density. This is just a one-line calculation. I'll let you work it out. So this thermal effective action, it encodes already here the entire equation of states of your system. Pressure as a function of chemical potential and temperature. But it also encodes more. It encodes any static response, right? This was for a very simple situation of constant chemical potential, but now we can consider what happens when we take derivatives. So for example, one thing we can compute from this is the charge susceptibility. As a function of wave vector. So this is the charge two-point function at 0 Matsubara frequency. Well, that's one way to get the susceptibility, but finite wave vector, which let's see, which I can get from this expression over here. So I'm going to Fourier transform this expression. I think I need to divide by beta. Okay, and if you take this derivative, these functional derivatives of this object, I'll let you do this in your own time, but it's not very difficult. You'll find the following. You'll find that you get a leading contribution from F0, the leading term in our effective action. And F1 will give a Q² correction to the susceptibility, and so on. There would be higher order in Q terms. Okay, so at Q equals 0, we see that the charge susceptibility is indeed what you would expect it to be. One derivative of pressure with respect to chemical potential is charge density. A second derivative, so we just have a second derivative like this. Okay. And generically, it has analytic corrections in Q², which are parameterized by these higher order Boltzmann coefficients. Okay, so this is equilibrium thermal dynamics. This results relied on the finite thermal. Okay, this was an assumption in establishing this thermal effective action. This result, and especially the analyticity of the susceptibility at 0Q, crucially relies on finite thermal correlation. Okay, as you know well, you would have non-analytic small q behavior either in ordered phases or in critical phases. Very good. Yes, question. Okay, yeah. So linear gradient term would be a total derivative, right? Because if you had a function, let me call it 1/2 your putative term. This I could write as dx of some other function of chemical potential. So that would be a total derivative that vanishes. Okay, but you do make a point that I wanted to stress here. For simplicity, I've assumed the system is isotropic. If it weren't, I would be allowed to have use partial x and partial y in different.
If I have a thermal gradient.
Yeah. Yes. Yes. Yeah. Yes. Yeah. So you can. I'm not saying you can't turn on a term with gradients, but it wouldn't appear in the local thermal effective action. So there isn't. Basically, the only thing I'm saying is that the charge susceptibility doesn't have a linear in Q term. Okay, in equilibrium. Yes. The interpretation of it as pressure, yes. Yeah, so you could ask, what if I had sorts a completely different operator just for fun? I could have done all this. I would have given them the same name, but it wouldn't have the interpretation of pressure. That's the only, so the connection to usual thermodynamics. Okay, so this is equilibrium physics. Now we're going to turn on to out of equilibrium. So here we saw that in equilibrium, we have this very nice organizing principle, very simple, of a local thermal effective action that has basically no degrees of freedom. It's just a functional of the background fields and it's local, so it's nice and simple. We'd like to find the organizing principle for out of equilibrium physics, and we'll see it's very different. There will be degrees of freedom, and there will be the hydrodynamic fields. But we'll work, we'll up towards hydrodynamics. Okay, so what I want to start with is a very simple argument to convince you that at finite temperature, when we start looking at things in time, in real time, you inevitably have long-lived excitations. Okay, and so the argument is very neat. We'll consider the retarded Green's function of a charge density or a conserved density of a conserved density. Okay, which could charge density, it could be energy density, spin density, whatever quantity you're interested in. I'm assuming at least energy is conserved, let's say. Okay, so this is now a real-time correlation function. You'll show in the exercises, you probably know this already, but that it's related to the Euclidean Green's function by the appropriate analytic continuation. And this object has the following nice property. Or interesting property. This object, or maybe its Fourier transform, has an interesting property. So let me consider the Rotary-Green's function of charge as a function of frequency and wave vector. It has the property that the limits of going to 0 and q going to 0 do not commute. Omega to 0 first. The charge susceptibility that we saw in the equilibrium setting. I'll explain why in a second. If we take the opposite order of limits, you get 0. Okay, so the left-hand side follows from the fact that that the Rotary-Green's function is just the analytic continuation of the Euclidean one. If you haven't seen before, you'll prove it in the exercise. So in particular, at 0 frequency, it's just equal to the Euclidean one at 0 frequency, which we were able to compute in the imaginary time, or in the thermal effective action, the equilibrium thermal effective action, and had a nice analytic expansion in Q. Okay, in particular, the leading term just measures the charge, the stiffness, charge susceptibility. On the other hand, the right-hand side simply follows from the fact that if you take Q to 0, the charge density at 0 wave vector is just the total charge, right? Which commutes with everything, commutes with the Hamiltonian, and it commutes with itself. Okay, so this object vanishes. Yes.
You mean about the retarding one depending on lots of bar frequency? Should that be?
So if I take my Rotary-Green's function and evaluate it at omega equal to a number, I omega n, then you can show it's equal to the Euclidean Green's function. It's a simple proof that I guide you through in the exercises. Other questions? Okay, so this non-commutativity, well, it's telling us that the Rotary-Green's function is actually not analytic in omega and q. Okay, at 0 frequency, it was nicely analytic in q. There was nothing happening, no long-range degrees of freedom. But when we start having time in the picture, the Green's function is not analytic. Yeah. Yeah. Yeah.
Pressure, you get equal tide correlation.
I think it's more of a zero Matsubar frequency correlation function. Now, there are in situations that these might be related, but yeah, I think this is how I would define kind of equilibrium response. But they're related in some situations. Yes.
Seems like you didn't need here that Q commutes to H, only that commutes to Q.
I want Q of T to always be the same thing, right? Yeah, it better be. Yeah. No, but it's a good point. The symmetries are crucial here. I need a conserved charge. Yes. So I'll be precise. Did I write hydrodynamics already? Oh, no. Okay. Yeah. For now, I don't mean much. For now, I just mean existence of long-lived excitations. We'll sharpen what we mean by hydrodynamics. Okay, so this non-commutativity of limits implies that we have some kind of IR singularity or some non-elasticity. At zero frequency as wave vector goes to zero. Okay. Now there are many ways to realize this, but I'll just maybe give you an example. In the case of simple diffusion, this non-commutativity is realized as follows. So this is a retarded Green's function of density in a diffusive system to leading order in small frequencies and small wave vectors. And you see that it has this non-elasticity. And this is what allows the two limits to not commute. Okay, if I take frequency to zero first, these things cancel. I'll get the susceptibility, charge susceptibility. If I take k to Q, this is what I called Q. If I take Q to zero first, I just get zero, which I should because it's a conserved charge. Yeah.
My comment was about correlation.
Yeah.
It's the equal time correlation function.
Yeah.
Which is has to be equal time.
Yeah.
Which is integral over
Yeah.
omega, and that's the imaginary part of this.
That's right. So if you take this and you compute the equal time correlator, you will get the susceptibility again. That's right. But that does rely on, there may be more assumptions there. Yeah. Yeah, that's right. That's why I want the retarded Green's function. But it's true that these same objects appear in many correlation functions, which is the power of hydrodynamics, right? It connects many observables. Yes. Yeah. Yeah, so here I'm being a little bit vague. Indeed, to be more precise, you could say the frequency of the pole. This argument doesn't tell you there's strictly a pole and not a branch cut or something else. So, it could, but there's certainly something happening. There's some non-elasticity in omega, which is going to zero frequency as Q goes to zero. Okay, yeah. But indeed, here it happens as a simple pole where omega of Q is just I dq squared. Yes. It doesn't tell you that you can only have diffusive poles. You could have many other things. So it depends what you mean by gapless. So here we're in a finite temperature context. You can ask about how things decay in time and space. Things are decaying in space, I'm assuming. But they're not. But the crucial point is that generically they don't decay in time fast because of this argument. Yeah, diffusion is an example. There are many things that will realize commutativity. It's probably the simplest example. So okay, so this isn't meant to be a proof of hydro. It applies to free theories as well. But I think it already shows that you have to have long-lived excitations at finite temperature in time. So the behavior in time is very different from the behavior in space. Okay, generically in space things decay exponentially, at least not in ordered phases. Whereas in time, generically they're going to decay much more slowly because of these singularities, these IR singularities. So the physics will be very different. And one more argument as we inch ourselves towards what hydrodynamics really is. Is the fact that, and you probably saw this in several of the other lectures, that the quasi-particles that we're used to, for example, fermionic quasi-particles in a Fermi liquid or in another phase of matter, typically acquire a finite lifetime at finite temperature, right? Typically acquire a finite lifetime in the thermal states. Even if they were stable at 0 temperature, they will generically have a width, we could call this thermal broadening, at finite temperature. Okay, for example, in an interacting Fermi liquid, even just the interactions of the fermions with themselves will give a finite lifetime to the fermions. Okay, through this diagram. So if you compute the Green's function of the fermions in perturbation theory, let's say, or otherwise, it's nice to package the result in terms of a self-energy. And in a Fermi liquid phase, this self-energy, let me evaluate it at Kf, has an imaginary part which depends on temperature, on T squared. You've probably heard this before. You've even computed it with Maslov. I don't know if he made you compute this diagram. Okay, so this is just kind of thermal broadening from, so this part here tells you that the quasi-particles aren't quite stable even at 0 temperature. Okay, but it goes to 0 faster than omega, so we still view them as sharp excitations. But this piece here goes to finite value at 0 frequency. So it tells you that these particles actually decay. Okay, their 2-point function decays in time exponentially. Okay, and this is extremely general. Even in situations where you might have thought you had the most stable quasi-particle in the world, even if you, so, Fermi liquids are a bit special because the quasi-particles do have a kind of finite, width at 0 temperature. But even if you have, let's say, a gapped excitation, okay, an optical phonon in a world with only optical phonons, this will have 0 width at 0 frequency, right? Because you can't, you don't have enough energy on shell to excite a multi-phonon continuum. But at finite temperature, you start populating these states, and you'll have a width. Okay, so this is basically inevitable. Even stable quasi-particles like a gapped excitation have thermal broadening. Actually, one exception is goldstones for reasons that we'll come to in a bit, but let's not talk about that yet. Okay, so this is very general. So we have two statements that are almost in contradiction. On one hand, I told you that things decay slowly in the thermal state. There has to be long-lived excitations. Okay. Now, on the other hand, all the particles we like seem to want to decay exponentially fast. So there's a slight tension. Yes. No, the dependence on T is highly non-generic. In fact, in the exercise, you'll study broadening due to an optical phonon. And here you'll find, so this is what's responsible for linear in temperature resistivity of normal metals at very high temperature. It's a simpler calculation than this one, so that's why I put this one in exercise. So yeah, the T dependence is very interesting and depends on details, the mechanics of what's happening. This is the result for Fermi liquid interacting just with itself, clean Fermi liquid. Yeah, that's right. Thanks. Yeah. So imaginary part at zero frequency, let's say KF for Fermi liquid, or whatever the relevant thing to do is non-zero. Yeah. Thanks. This is an example, but this is the very general statement for any interacting particle. So yes, question. Yeah. Yes. Yes. Yeah. That's right. So right. The question was about non-interacting Fermi gas. That's true that you would have something that looks like a lifetime. Yes. Yeah. Yeah. So I'll talk a little bit about the distinction. Whether you should think of that as a thermalization time or not in the very last lecture. Yeah. But yeah, I'll mostly be talking about interacting systems. So clearly in a non-interacting Fermi gas, the Bloch states are not the right eigenstates, but there's some eigenstates. It's still a single particle problem. Okay. We'll talk more about this in a minute. So this tension tells us that the long-lived excitations are necessarily collective. Okay, they're there because of the conserved densities. Basically, the conserved quantities decay slowly, as per this argument, or just because they're conserved. But the quasi-particles we started with typically decay exponentially in time. And so if you wait long enough, you don't have quasi-particles anymore. You might just forget about them. You only have these collective excitations, okay, conserved densities. So this motivates building an effective late time description that only has these collective excitations with only these degrees of freedom, the densities. Okay, conserved densities. Okay, and this is what I will be calling hydrodynamics. So maybe an important point is that I'm not assuming momentum is conserved. I just need one thing to be conserved. Let's say energy density. So it's a very general statement. In any interacting system, at finite temperature, at late times, it will be described by effective. You expect it to be described by an effective description of these densities. Yes.
So I like to recap to try to. So you're saying that the existence of a long-lived excitation is because these two limits don't commute.
Yes.
And that means you have some pole.
Right. Some non-elasticity. Yeah.
But so what's the statement that I don't get why this has to mean that the pole doesn't have a lifetime or doesn't have an infinite lifetime?
Right. So okay. Yeah. So the pole, in fact, looks a little bit okay. Let me maybe put the I over here to make it look a little bit like that expression. Okay. So like this. So you might say this looks a lot like this lifetime we had for the quasi-particle, right? We have an imaginary part that looks a little bit like a self-energy. But the key point here is that this lifetime is going to 0 as Q goes to 0. Okay. And so when you Fourier transform in time and space, you won't get, so if you just Fourier transformed in time, you would get exponential decay with rates dq squared, right? But if you also Fourier transform in space, you'll have polynomial decay. Yeah, so that's the important point. So right, this was also important here. It's basically the statement that it when omega goes to 0, or distance away from kf goes to 0, this does not go to 0. Okay, unlike that. Yes. Yeah. Okay, yeah, let me, yeah, so the question was that quasi-particles are already collective in some situations. That's true, yeah. So here I mean collective, even more collective. Collective built out of the quasi-particles, okay? So you might have found a nice, maybe zero temperature description of your quantum phase of matter, which involves already collective excitations. I'm saying even those are actually going to be short-lived at finite temperature. What is not interacting? His quasi-particles?
No, he's super collective.
So that's a good question. So they will be interacting, but they will be the right degrees of freedom in a sense. They'll be long-lived. Yeah. There was also a question. Let's start here and then.
So if I have a random walk,
yeah,
that also would be by this kind of.
Yes. Yeah.
And there is no collective force.
That's right. That's right. So that's not what I would call hydrodynamics. Yes, I would not call that. That's right. Diffusion can arise in single particle physics, and so there are situations where it's there's a bit of both. The boundary is a bit obscure, but we'll talk about this in detail in the third lecture. There was a question over here. Yes.
Actually, maybe a bit related to that. When you mentioned classical phase transitions, you talked about classic work to do with dynamics there. But that dynamics was some Markov chain that's equilibrating to that given measure, right? You phrased everything as some closed quantum system which is undergoing, quantum evolution with some Hamiltonian, and I have some collective modes that are evolving.
Yes. Yeah.
So, what's the connection between two kinds of dynamics at finite temperature?
Right. So most many-body systems act as their own bath, and so you don't really need to put in noise by hand. Sometimes it's a technical crux that can help. Sometimes you're actually studying an open system, and you might want to do that. But most many-body systems we're interested in actually act as their own bath, and so they thermalize even if they're closed. Yeah.
But that distinction is not important with hydrodynamics as long as, for example, the Markov chain has the right symmetry.
That's right. Yeah. So there's I'm assuming the system is closed, but you could lift that assumption with some and still get similar physics. Yes.
So your example, use the right from order. Don't you test out the interaction of this?
That's right.
In this case, is this belongs to the description of the hydrodynamics?
Yeah. So that there was that question before. So I will not call that hydrodynamics, and I'll make this precise in the third lecture.
But it still have a
right, but it's a single particle. It's single particle quantum mechanics. So it's different physics, and I'll make this distinction more precise maybe in the third lecture. Okay, maybe let's move on. So we'll really, next lecture we'll really start working on these effective field theories of hydrodynamics. Before that, I want to just give you a little primer on how to do quantum many-body physics, quantum field theory directly in real time. Using the Schwinger-Keldysh method or contour. Okay, and you might ask, why do we need to do this? We just saw, or you will just prove in your exercise that real-time Green's functions, like the retarded Green's function, can be obtained by analytic continuation from the Euclidean one. So let me just always work in imaginary time. Well, there's several problems with that, and I mean the main problem is that in systems of interest we won't be able to actually solve the Green's function exactly. Okay. And so we will only have access to it, as we'll see, in some regime, in a late time regime or low frequency regime. Okay, and how that maps back onto the thermal cylinder, onto Euclidean times, is very non-trivial. Okay, and there's no it's very difficult, unless you have the exact analytic expression for the Euclidean Green's function, to know which piece of your imaginary time, where time is always less than beta, corresponds to my time much larger than beta physics. This is also a problem that a lot of the numerics faces. To have the analytic expression. Okay, because the effective field theories that we'll be working with, these effective field theories of hydrodynamics will apply to late real times. They basically don't have a formulation in imaginary time. Okay, there's no way to formulate hydrodynamics directly in imaginary time. You can do microscopics in imaginary time, but you just can't do. You can't do hydrodynamics in imaginary time. And so this, I think, is really, well, at least for me, a big motivation, why you should learn this extra formalism that you might have thought is otherwise unnecessary by analytic continuation. Okay, so how does this work? So we want correlators, functions in real time of various observables. And because so what we're doing here is that now we need to study time evolution in a mixed state, okay, to compute something like this. So we need to time evolve a mixed state. And so time evolving a mixed two unitaries or two legs. Unlike when we study state physics, where we can get away with just one time evolution unitary. Okay, so we'll have two legs. And what we'll do is very similar to what we did in the equilibrium thermodynamics. We're going to construct a generating functional for this object. Okay, so here, yeah, actually, this equation is not very good. This is the thermal density matrix. These are my operators. The thermal density matrix commutes with the Hamiltonian, so this is not a very good equation. Okay, yeah. So let me be a little bit more precise, actually. Yeah, maybe you could just say, well, okay. If you viewed these operators as perturbations on top of the state, then the state would actually have non-trivial time evolution. Yeah, the full row, yeah. But let's be a little bit more precise, indeed. So the object that we'll consider to generate, we wrote it just for Euclidean correlators, but to generate real-time correlators, again, we'll couple to sources. Let me call the source J. And we'll take derivatives with respect to these sources. So in the presence of these sources, the time evolution operator not just e to the IHT, right? Because the Hamiltonian is time dependent. So instead, it's the time ordered exponential. So time evolution unitary from some initial time Ti to Tf with arbitrary sources has the following formal expression. It's a time ordered exponential. And so the object that we'll consider is the following. We're going to time evolve both legs of the density matrix and then take a trace. And to not get zero, I'm going to put different sources on both sides. So I'll time evolve from -infinity to infinity just so that I have the power to generate correlation functions at any time. Okay. So this is the more precise object that we're going to consider. And so pictorially, you could draw it in this way. We have a density matrix. It has legs. I'm time evolving the left leg with the unitary operator for J1. So time goes like this. Then I have a trace. So trace tells me that I impose periodic, I identify fields at this point. And then I time evolve back with a different source. Okay, this is just a formal object, but it's an object that we'll be able to use to generate all the correlation functions we care about. Yeah, thermal. I'll take thermal, yeah. Well, that's right, but you won't be able to do much with it. But yeah, you could consider a different state. That's right. This is how you would time evolve a general density matrix. Yeah, so they're just different sources. So for example, two experiments, okay? J1, I don't know who asked the question, but you asked the question. Yeah. Okay, no, sorry, who asked the question? Oh, you asked the question, okay, yeah. So they're just two different sets of sources, okay? It's an artificial construction. I'm talking to one experimentalist over here and a different one over here, so they're turning on different sources, okay? I want them to be different. If they were equal by trace cyclicity, this would actually just be trivial, right? It would just be one, right? That's why, so I'm just constructing this object. And in fact, you've just identified that it has following general property. If I set the two sources to be equal, I'll just get one, right? So this is not a very interesting object. Basically, if the sources are equal, the time evolution here is exactly the same as the time of there. And so they completely cancel each other. So the whole contour collapses. It's the collapse rule. But you could say it's just from trace cyclicity. There's another general property that it has. It's not a pure phase, but it has some simple reality condition, which is that if you take the complex conjugate of this, you're going to swap the two sources. Okay, you could say this comes from unitarity. Now, these two conditions are completely general. As Leo said, you could have used any density matrix. These apply for any row, but we will be interested in a thermal density matrix. For example, e to the minus beta h. And in this case, there's another property. Which comes from the fact, again, that e to the minus beta h is like evolution in imaginary time by I beta. There's another property called the KMS condition. Which looks like this. That the partition function and the partition function evaluated at sources that are slightly shifted in time by an imaginary amount is equal, okay? This is derived carefully in the notes, but the intuition is very simple. You just commute this across here. It shifts every operator in here by imaginary time by a little amount. And then what I did here is that I also acted with time reversal symmetry, just to put it back in a form that looks like this. But I'll let you look at the notes for the derivation. So this is special for the thermal states, and it's called the KMS condition.
Say again, the intuition.
Yeah, so the intuition for this is that when the density matrix is this, then you can actually take it across here at the cost of evolving any operator in this unitary in time by I beta. Okay, and then you can absorb this shift by shifting, changing the t, and you'll get a shift in the sources. Well, I would say from the perspective of this construction, it's almost a trivial property. However, it has interesting consequences. We'll see that fluctuation dissipation theorems are follow from. So there's some things that may seem non-trivial from other approaches that are much more straightforward here. But yeah, here it really just comes from H being H. Yeah. That's right. Yeah.
If I want to keep the connection to the stochastic dynamics.
Yeah.
It seems now that like the you coming from A to really crucial.
Yeah. Yeah. Yeah.
Yeah.
No. So that
analog these things. If I'm just evolving with a general.
Yeah.
That's a detailed.
Good. No. So there. In fact, yeah. So that's a good question. Another very good motivation for working in real-time, quantum many-body physics with this contour is actually open systems, where you have Lindbladian dynamics of density matrices, and there, obviously, the time, but you would still have a very similar picture. You have a Lindbladian that takes you here, and you could, you could also construct a generating functional in this context. Actually, I could have been more general to include that.
But what's the analog of KMS condition then?
That's right. There wouldn't necessarily be. Although there's some experts in the room, you'd have to ask them. There might be some remnants, but at least the naive KMS condition won't be there in that case. Yeah. 10 minutes. Okay. Very good. So with this object, we can now generate, correlation functions in real time. By taking derivatives. Okay, and what this will do is that it will pull down operators in a way that's time ordered on the left and anti-time ordered on the right. Okay, so it's a set of real-time correlation functions that it will be that we can generate with this contour. Okay, and maybe just to simplify this notation a little bit, the way I'll write it is when an operator is on the left, I'll just use the one index. So we have our two contours. Contour we have source one, contour where we have source two. Okay, and I'll just use a shorthand notation for these correlation functions by giving a 1 and 2 index for the operators themselves. Okay, so these are really the objects that we're computing in human readable notation that you're used to, but I will sometimes use this shorthand notation. And a final piece of notation. It's convenient to consider not just 1 and 2, but the average and difference, sometimes called Keldysh rotation. So the average fields or operators and the difference. I'll give these subscripts R and A for obscure reasons. And this basis is pretty nice because it has the nice property that in any correlation function that has an A operator at the latest time, any such correlation function vanishes. So if I have a correlation function with a bunch of R or A fields, and the very last one is an A field, then this correlation function is just by trace cyclicity, right? So we're generating correlation functions of a bunch of operators. But the very last operator in the correlation function, I can put it either up or down by trace cyclicity, right? There's no difference between this correlation function and this correlation function, right? The latest operator here could also be the latest operator here. It could be 1 or 2. It doesn't matter if it's 1 or 2. So therefore, if it's A, if it's 1 minus 2, you get 0. Okay, so any such correlation function vanishes. Okay, so now we're ready to relate these things to observables you know. So, for example, of these fields are related to familiar Green's functions. For example, let's look at. Yep. Yep.
So the generating function is, convenient because you can generate.
Yeah.
Any kind of Green function you want.
Right.
That order, the end of that order.
Yeah.
But it doesn't really come from, like that evolution operator.
Yeah.
If you really turned on a J, like a background J.
Yeah.
There's no way to generate this.
Yeah. Yeah.
Just a JFT, and if I evolve it by UU that.
That's right. That's right. Physically, yeah, there isn't an experiment that corresponds to doing literally this. That's right. That's right. Yeah. So this is more of a formal construction to generate these things. Yeah. Yeah, you can, after the facts, you can figure out which experiments would get which Green's function, but that's right. That's right. Yeah, yeah. Except in an open system, Lindblad dynamics. But yeah, that's right. So let me just give you an example. Let's compute the RA correlation function of the operators. So what this means, I'm just translating back to a notation. So R is the average field. A is the difference field. So I'm going to have a bunch of terms. O1 of T, O1. O2 of T, O1. 1 of T, O2 of T. 1 of T, O2. And O2 of T, O2. And what these things mean, if I use this dictionary over there, so this correlation function is a time-ordered correlation function. Take up some space. Of the O operator with itself. Okay, that's what O1 of T, O1 means. Okay, it means they're time ordered. This one, however, the 2 is always after the 1. Okay. You always have the density matrix, first the 1, then the 2. Okay. So the second correlation function means something slightly different. It just means trace rho. We first have the operator at 0 and then the operator at T. Similarly, this one, the 1 is always before the 2. So we have O of T first and then O. And finally, this one is anti-time ordered because they're both 2. Okay. So this thing will equal to will have a different expression whether t is positive or negative because of all the time orderings. Yes, question? Yes. Here, that's a good point. So the question was about, if O is a bosonic operator. Here, it's a bosonic operator, yes. Fermionic operators are left as an exercise. Yes.
How the second term comes about?
This or here? How to go from here to here?
That.
Yeah, okay. So let me explain. Yeah. So what this thing means, this is just a notation to mean that I have, when I have the 2 index, it means that it's on the right of the density matrix, okay? And the 1 index means it's on the left, okay? Let me shift the density matrix all the way to the left. So the 1 will always come first and then the 2, okay? So this means that I need to put this guy first and then this guy, okay? So O of t. And let me contrast it with this one, O1, O2. I always have to put the 1 first, so it's O of t, O in this case. Okay, maybe let me just finish this this calculation. So the subject here, depending on if t is positive or negative, will look different. If t is positive, then this time ordering does nothing, right? It's already time ordered. This anti-time ordering flips them. So we actually get this term twice and this term twice. Okay, so we get a commutator. So if t is positive, we get twice a commutator of the 2 operators. If t is negative, then this would, the O of t would be to the right. And so it would actually cancel this term over here, okay? And here this O of t would stay to the left because it's anti-time ordered, and it would cancel this guy over here. So we actually have, it vanishes if t is negative. We already knew this by the latest time condition, okay? If the latest time, which here is 0, is carried by an A field, then the correlation function vanishes. Okay, so, and this is just the retarded Green's function. So we find that the RA correlator is just the retarded Green's function up to some factors. Okay, and I'll let you similarly show the other ones. So the AA correlator, that one is just always 0 because there's always an A field carrying the latest time. And the RR correlator, if you spell it out, involves an anti-commutator of the operator, and it's what we usually call the symmetric Green's function. Okay, and you might be familiar also with, in fact, I'll show this in the exercises. These Green's functions are related. In fact, I didn't write the relation in my notes, so I'll probably butcher it. By what's sometimes called the fluctuation dissipation relation. In this case, it would follow from the KMS condition. Okay, maybe I'll stop here.
A operator A comes last.
Yeah. Yes. Yeah. So the A operator is at time 0. The R operator is at time t. If t is negative, then I have A operator at the latest time. So it should vanish. Yeah. So there's a latest time. Yeah. Okay. I think maybe this is a good place to stop, and we'll continue.